solution. So the length here, the total length, is 2 pi r, right? And that must be equal to some integer number times the wavelength. Then if this condition is met, then what you have is that wave which coming back exactly at the same phase that it was before. So it stays there as a stationary wave and can be captured and live forever. There is no dissipation in the system. So this is a condition for different lambdas which can be there, right? So what it means is that you can only have light which has inside the ring, which has wavelengths given by 2 pi r divided by any natural number, 1, 2, 3, 4, 5. So you can fit here 1, 2, 3, 4, 5 wavelengths. And now for very small numbers n, when you try to fit only one wavelength, there is some corrections, but we will not care about them. It's the full solution becomes a little bit more complicated, so we'll skip it. But then what you have is your wave number, which is 2 pi divided by lambda n, right? It's for n, for any given n, you have particular lambda. For that particular lambda, you have particular k, and the frequency is given of that wave is given by the speed of light times this wave number. And so what you have is just this relationship, and if you now plug that lambda n into here, what you find is this is c divided by r times n. Right? So what it means is that only very particular frequencies can be fit into a ring which has radius r. All other light, if you try to squeeze it inside it, it will not stay there. It will interfere itself to 0, and you'll get nothing. All right. So that's the full solution. That's the frequencies which are allowed in this ring. That's a typical story of a resonator. Now, if you have some dissipation in the system, that will change it a little bit, but nevertheless, that's the first approximation to this story. Right. Now, I give those problems that and the second one exactly because when we're going to go through quantum mechanics, that's exactly the same effect in quantum mechanics. That's where those states, if you have heard about quantization, right? Quantum mechanics means quantization. That's exactly the same thing. And that law a little bit different, but the fact that you need to fit some wavelengths and there are some frequency, only very specific frequencies, that's exactly what quantum mechanics is all about. Now notice that it is very important here that you have phase on the wave. The wave has a phase, so it can interfere, is constructive or destructive. And that's the origin of the quantization. All right, so the next question was pretty much the same, but now it's not light, it's some strange wave which has some particular dispersion relation, and that dispersion relation was given by omega equals some number h squared divided by 2m, and then there is k squared. Now, if you think about it, that if omega is your energy and k is your momentum, that this is energy is proportional to momentum square, and this is very close to the standard particle dispersion relation. So just energy equals p squared over 2m. So that's 2m actually given here. And that's again for the reason. But now what you have here is two mirrors, and you need to fit a wave inside, right? So in order to fit a wave there, so what you need to do is to have this is one situation, right? That's how the wave will be fit inside, or you can fit the wave which has, so this is half of a wavelength or full wavelength, right, and so forth. Right? Now, if you think about it, this is exactly the same story as if you play guitar again. Like if you think about this as a string, right? That your tone of the note, if you just plug the string, it's when the half wave half wavelength of that sound wave is fitting inside the string, that string, and that's your tone. This is when full wave is full wavelength is fitting inside the string, and that's if you play guitar, that's it's called harmonic, right? If you take a 12th fret and then dump it a little bit, and you can have one octave higher sound on the same string. So that's exactly the same story. But then it tells you immediately that if this length is L, then what you need to fit in is that L equals, you need to fit in the integer number of the half wavelength. So first half wavelength, and the total length, it's 2 halves, right? The 3 halves, and so forth. So that's exactly what you will have. So that's the story of quantization of lambda. Only the light of the wave of that particular wavelength can which satisfies that relation can fit in. Right. So then of course what you do is you say that your k now is 2 pi divided by lambda n. This is the k. This is the wave number for such wave, which is then 2 pi divided by 2l to ln, right? And then all we need to do is to substitute it over here, and what you will find is that omega n equals h 2 pi h 2 pi h bar squared divided by 8 ml squared, and here we have n squared, right? So then your frequency is not going like first power of n, but it goes like n squared, and again you can fit only some very specific waves inside this resonator. Right. Again,
can you go over the k value again? How did you get that?
Well, k is always just 2 pi divided by lambda n. It's actually written on the first problem. Right, so
and that's always true for every wave.
Yeah.
Okay.
The wave number is the following thing. So if you have a wave, right, sine omega t minus kx, right? That's your wave. But then this is your wave number, right? But this wave number must be 2 pi divided by lambda, simply because when x changes by lambda, the total phase inside this argument, the total argument must change by 2 pi. So the sign returns back to where it was, right? So you see that if I now add lambda to x, then k times that addition lambda will give me exactly 2 pi.
Okay.
So it really doesn't matter what you consider. It must be so. All right. So that's those two first questions, first two problems. And again, what I want to emphasize here, I do always give homework problems for a reason. I don't just give exercises. So that particular problem was sort of leading to the very same story in quantum mechanics. In quantum mechanics, we will see that exactly what I've just done here will be exactly done the same way in quantum mechanics in order to see the quantization of some levels in some potential levels. And I'll talk about it a little bit more, but I just want to tell you that it's really not a property of quantum mechanics per se. It's a property of any wave. When you have wave, you have a phase, and if you have a phase, you must match the phases in order to have something real. Otherwise, those waves will interfere with itself, and in a resonator condition, it will interfere itself to zero. And this is a property of the phase, and the phase is a wave. Right? Whatever has a phase has a wave. It is a wave. So it's basically the major difference between waves and particles. Because for particles, you don't really have anything like that, right? The particle can travel here with any velocity whatsoever. It doesn't really matter. For wave, it does. All right, so that's. But we'll talk about it more and later on the context of quantum mechanics. But this one was just to sort of figure out for you why phase is important. All right, the next question was the following: that you have electric field which is produced by some charge, and or you don't really need to think about this electric field. This is some coefficient, doesn't matter what it is, really, and that wave is given by depends on distance from some point. According to this field, depends on the distance from some point 0, which is it's the origin of the coordinate system, according to this law. So what it tells you is that if you have origin of the coordinate and any place. So here's my origin. This is the place where I measure my field, right? So it's that point has a radius vector r, right? And then this, well, what this law tells you that field here E will be pointing in the same direction as r here, right? And its magnitude, the magnitude of that field E will be equal to k divided by r squared, right? Because the magnitude of r is of vector r is r, so 1r from here cancels 1r from here. You have k divided by r squared, and that's exactly what Coulomb's law tells you, right? That's Coulomb law. Usually that k is multiplied by the charge here. I just say that the charge is included in this k. It's just some number, because eventually I get 0. It really doesn't matter what kind of number I put there. So then what you need to do is to prove that divergence of that field equals 0 at any point, and any non-zero point. Now, this is a very, very important story here, that this is incorrect for r equals 0. Exactly at the origin, you actually cannot perform this calculation, because exactly at the origin that E diverges, E equals infinity, and there is no way to differentiate infinity. Infinity is not a number, right? So you cannot do anything with it. So you cannot actually take the divergence exactly at this point. And that's very important. That's the origin. That's why this point here is the source of that field. I'll talk about it a little later today. And so now all we need to do is to compute this expression. And that expression is what? Is it dEx by definition over dx plus dEy over dy plus dEz over dz, right? That's what we need to compute, and we need to show that it equals to 0. So let's do that. Ex equals, now we assume that there is some system of coordinates here, x, y, and z going your way. So Ex then equals to k. The x component of vector r is x coordinate of this point, right? And here we have r cubed, which is x squared plus y squared plus z squared, and square root and then cube, so it's 3/2. Right? So now we need to do dEx over dx. So we need to take this function and just differentiate it with respect to x. X here in 2 places, so we need to differentiate both. And what you have here is, if you just differentiate this one, you get k divided by x squared plus y squared plus z squared 3/2. And then you need to differentiate this one, right? It will give you minus 3kx squared divided by x squared plus y squared plus z squared 5/2, if I did it correctly. Yeah. All right. So let me write it the following way. So this is my r squared, right? So what's written here is k divided by r cubed minus 3. That 3 is very, very important here. Minus 3k x squared divided by r to the 5th. Okay. This again. This is square root of r squared, right? So that's yeah, square root of, this is r squared, sorry, then I have five halves, it's fine. Now it's always a good idea to check units in this situation. The units of this, so those two terms must be the same, right? Well, k has some units and it's the same, so we don't need to worry about it. Here we have 1 over length cube. Here we have length squared on top and length to the fifth on the bottom, so it's 1 over length cube also. So then the units of both terms match. That's the easiest way to capture if you made a mistake somewhere in those powers. So this is dE over dx, right? But then what? But the rest of them are exactly the same. So the difference between ex and ey is that instead of x there will be y here. But then it's exactly the same story, and with z also. So what we will have then is for all three terms, we don't need to do any differentiation here. What we have is the following bunch of equations. 3 minus 3 x squared divided by r to the fifth dE y over dy equals k divided by r cubed minus 3 y squared divided by r to the fifth and dEz over dz equals k divided by r cubed minus 3 z squared divided by r to the fifth. Right? I basically just substitute instead of x here. That's the only place where which knows about x. Instead of x, I put here y and then put here z. That's all. And now we need to sum them up. According to our prescription, right? This one, we need to sum up all those derivatives. And so if I do that, what I will have, I'm just summing up those, right? So what I have is just divergence of E equals, well, I need to sum up those first, and I have 3, you see that, again 3, divided by r cubed here, minus, now I have 3 here, and I have x squared plus y squared plus z squared on top, divided by r to the fifth. But x squared plus y squared plus z squared is exactly my r squared. So I have here, and k also, k r squared. Right? Oh, I forgot k. Sorry. Wait, no one tells me. Come on, guys. If I make such a stupid mistake, I would really appreciate if you tell me. All right, so then, and here we have r to the squared on top, r to the fifth on the bottom, so they cancel each other, and what I have is this one. And now I see that they exactly cancel, those two terms exactly cancel each other. Right? So it is 0. So this particular, notice that this particular field is such that it is not 0 anywhere, the field itself, but its divergence is 0. Okay, that makes sense?
Yes.
Any questions? It's a Coulomb interaction, right? So this is your electric field. So the major point about the electric field, and I'll talk about it today a little later, that the divergence of the Coulomb field equals 0. Okay, that I'll talk about. Okay, now again, I want you to really understand that divergence equals 0 only in every finite point. What is divergence of this electric field in the origin of that? What is the divergence of that field in the origin? That question makes no sense. It does not exist. That object cannot be computed in the origin. So whatever happens, in a sense, in the origin, we have a singularity of that field. And how do we deal with that singularity and how we account for it is a different story. And I'm going to talk about it today a little later. All right. So it's the divergence equals 0 everywhere except one point. Okay. That makes sense?
Yeah.
All right. those problems, you know, when one point in the whole space changes everything. All right. So, and there was another next problem was just a fun problem of this kind. So you had a following circuit. You had resistor here, then resistor here, then you have resistor here, and again resistor here, and you continue it forever to the infinity. Right? And each of those resistors has resistance capital R, and you need to compute and all of them. And you need to compute the resistance between those 2 points. And so that was the question. And there is very standard way to solve this problem. And in fact, that standard way we get extensions to many other things. And it's in a lot of cases, in quantum field theory, when you computing some Feynman diagrams, like something which like sort of looks like very high and then very complicated stuff, right? And what you do there is do exactly what the same kind of trick with your computation. It actually has its own name there. It's called Dyson equation. But it's in reality it's the same thing that you can do here. So and the trick is the following. Let's imagine that resistor is R, is known. So let's think about it. We already solved this problem. Right? Then you see that it's semi-infinite, right? It goes to infinity. So if I take now this circuit and I add one more element to it, like this, right? And again, this is R, this is R. Then nothing has changed. It was semi-infinite before, it is still semi-infinite now. Right? And it has exactly the same structure as before. In fact, if I draw those two circuits with this element and without that element, you will not be able to tell which one is which. Because you cannot count them, it's still not infinite. I mean, you cannot count to infinity. Unless you are Chuck Norris. Sorry. So it means what it means is that the resistance here must also be R. Right? But remember that before that R little r, we call the resistance between those two points when everything disappeared. So instead of this circuit, we can put in the same little r. Right? And then I have a very simple circuit here. This one resistors in series and those two resistors are in parallel. So then what I have is R equals the resistance here equals this R plus the resistance of two parallel resistors, which I happen to remember what it is because I derived it yesterday. Here you go. Okay. And this is our equation for R, for little r, which we need to solve now. So R will be such that that little r will be such that this equation is satisfied, right? And if you do that, so how you do that? Well, the easiest way to manipulate those things which I found is the following: that you move that capital R on the other side. Now you multiply everything by this one. Right? Now this is easy to open up, so it's R squared minus capital R squared and minus RR equals 0. Or to write it in canonical form, I need to write them in different order, and then it's RR minus R squared. Right? And now what I see is a quadratic equation, and quadratic equation is something which I can solve. And the solution is that little r equals capital R times 1 plus or minus square root of 5 divided by 2. Now, at this point, you need to stop and think about, well, one possibility here that I cannot have two answers for the same resistance. And not, but here I have plus and minus. But then you look at that and say that the square root of f is larger than 1, right? So if I pick here minus sign, then my resistance becomes negative. Negative resistance does not exist. It's not a resistor, right? So it means that I need to drop that minus sign. It's not physical. It's this particular problem. In some other problems, it's very, very physical, and you have to think about a lot about which sign to pick. But here we know that resistance must be positive because it's connected to dissipation, and dissipation is always positive coefficient in dissipation, and so we must pick the plus sign. So that will be the answer. That's the resistance which we'll be measuring in infinite, semi-infinite circuit. Any questions?
I have some questions about the first two parts.
Okay. All right. Go ahead.
Okay. So the first one is when it's asking for frequency of light, would we normally just solve for omega and not like f, which would be more like hertz? Because I don't believe that was clarified on the homework.
If it's not clarified, that means that it doesn't matter. I mean, any answer will work fine. If you put omega, I'll give that instruction to my grader that if you give answer in terms of f, that's fine. If you give it answer in terms of omega, that's fine. All right. I don't care really how you compute those things. I usually use omega because I'm not an engineer. If it's easier for you to think about in terms of f, the frequency, right, 1 over time, 1 over period, then it's up to you. It's okay. None of that.
Okay.
It's actually not important. Okay. And they're connected with each other by a factor of 2 pi. I mean, what's 2 pi doesn't have any physics in it.
Yes, thank you.
All right. So if it's not clarified, you always can ask a question. You could have sent me an email. I would tell you the same thing before you write anything if it gives you a problem, or just use whatever you want. I mean, it's as soon as it's frequency and there is a simple relation between what you computed, what's needed. Then I don't care. If I didn't specify it, it means that it's my mistake in the worst case scenario, and I don't take points off my own mistake. All right, doesn't make any sense? Any more questions?
Professor, in problem number 2, h was not squared, I think.
Oh, then don't square it. I'm sorry, I don't have the text of the homework problems right in front of me, so I don't remember what it was. Whatever it was, do it. I mean, my grader will be instructed to take those things as they've written. All right, so it shouldn't be any problem. Okay. So all right. So the main physical thing here is you said that I'm trying to teach you not. I don't try to teach you how to manipulate formulas or how to take integrals or something like that. This class is not about it. It's class about that whole pictures of what's going on in this world, all right, in physics. And the main message here is that the fact that you need to match a phase so that must be integer number of wavelengths. And if you got that point, then you got it as far as I'm concerned. Right? If you want to really know how to do the calculations, we solving equations, solving differential equations, and blah blah blah, taking integrals. Well, you need to take a proper class, not a modern physics class. It's I cannot fit all of those stuff, all those skills in 10 weeks. It takes about 10 years. All right. Any more questions?
So on the last question, it was positive because we needed to take account for dissipation, correct?
It is positive because I'm asking about resistance, right? And resistance is dissipation. Otherwise, it's not called resistance; it's called a battery. So it's if I'm asking for the resistance, then it must be positive. There is no way to have it negative, right? It's not a resistance then.
Okay, thank you.
All right. Okay, so now the next thing. Any more questions? Well, let me make one more comment. That plus and minus sign, the fact that I get rid of minus sign, is pretty much the only physics here. Right. The rest is just manipulation of that. I mean, that little trick of treating semi-infinite, and the fact that you to set to something semi-infinite, you add one more block, and it's still the same thing. It's a trick which is very useful, and it's fine. It's good if you know that or you figure it out. But the only physics, which is the only physical statement in the whole problem, is that the fact that you need to get rid of the minus sign, because that result with minus sign is unphysical. All right. Okay. Let me move on. And the next in my agenda is an announcement about the exams and exam procedure. I've sent the announcement through eCampus on that, and so if somebody didn't get it, well, let me know. I'll send it again. And if you have any questions, please ask. If you have some questions about the procedures, then it's absolutely, I'm absolutely sure that you are not alone. It's 70 people in the class. If you have this question, about like 10 more people have those questions, but they're afraid to ask for some reason. I don't know. It's probably my hair or something. So please ask those questions. If something is not clear, if you still need some clarification, please ask them before the exam, so you know what to expect and so forth, right? I cannot sit inside your head and think about what you have doubts about, right? It's you need to tell me. I try to write as complete as possible. Now the exam itself will have 3 problems, and it's very similar to the homework problems and to the previous exams or whatever. So it's all pretty much the same. I'm way too lazy to do something very different. So you'll have your time, and again, please make sure that you have everything ready on Wednesday. And so the only thing which I do require is that everyone is logged in Zoom, and so I can see that you are actually taking the exam. Now, I do think that requiring you to turn on your webcams is sort of violation of your privacy. I actually very, very uncomfortable with requiring students to do that. So I don't require that. If you want, you can do that. It's okay. But otherwise, I'm fine with if you're just there. Now, I know that it's and there are lots of discussions about those things right now, because this is the first time we actually do everything remotely, and especially exam remotely, and how to do that, how to prevent cheating, and so forth. I don't know the answer to this question. Again, I think that there is some also privacy concerns there, and I don't really think that it's a good idea to ask you to install a surveillance equipment in your own houses for me to be able to be sure that you are not cheating. So in the situations of that like moral ambiguity or whatever, I tend to trust people, and well, it backfired many times, but I'm still okay. And so I do trust the students do not want to cheat, right? Because now, if you think about doing it, then think about that who you're cheating on. You're not cheating on me. I'm already fine. Who you're cheating on yourself, and that's all. That's all you're doing. So please don't. Please do it. I don't give very complicated problems. I hope that the problems actually interesting which I give. So we'll do the best we can. All right. Okay. So that's enough. Again, if you have any questions about the procedure of the exam, please ask. Please do that. All right. Now let's talk about the content of that of the stuff, the rest of the material. Now the I made some pedagogical mistake in last lecture when I was talking about continuity equation, right? So if you have some current density and then the divergence of that current density equal plus rho dot must be equal to 0, right? This is plus, and that's a continuity equation. And I was saying that if this is a conservation law, this is a statement that whatever the current is, whatever that rho is, if it's charge or it's charge density and charge current density, if it's mass, the conservation of mass, this is mass density, this is mass current density, and so forth. Just normal flow of stuff. And this statement is a conservation law. The statement that that whatever we calculate cannot be created or cannot disappear unless it from inside any volume unless it goes through the boundaries. Right? That's the statement here. It's a statement of the conservation law. Now, it's pedagogically, it's always a good idea to say when it is violated. Right? And I made that mistake by not giving you an example, and I'm going to do it right now. I just want to make an excuse for myself. The fact that it's, as I said, this is a statement of conservation law, and conservation law is a very, very strict statement. Right? So I mean, there's only few things in this world which are conserved, and it means that it's very, very easy to make a mistake, because I assume that you sort of, for everything else, there are only very few things where that thing's working, but for everything else it doesn't. There is no conservation law that says the continuity equation will not hold. So it means that the majority of things are actually not a conserved quantity. So I try to give you exceptional example like charge and mass. But, pedagogically, it's actually good also to say when it is not conserved. So in not conserved situation, let's imagine that we are counting people, right? And now, so we have, what we can do, like people come and go all the time, right? They move around, and we can introduce by moving them around. It's exactly the same story that if we have a density of people somewhere and they move with some average velocity v at some small area, right? Then this is the current, right, of people now, and then density of people is, you can also, it's just number of people inside the area, and then we can ask whether this continuity equation will work for them or not. And in this situation, well, it actually turns out that it depends. It's not always correct, because the number of people is not conserved. All right, so if you have some area, right, and there is some hospital inside it, and this is now your volume, right? Then the number of people will not be conserved. Some people die in the hospital. Some people get born in the hospital, right? So the total number of people will not conserve, and then it means that the continuity equation does not necessarily hold. Now, if some other situation when those processes of dying and giving birth to people can be neglected. For example, if you're talking about like something around the pizzeria, right? People usually don't die in pizzeria, and they don't give birth in pizzeria, as far as I know. And so it's then it will be conserved, right? But not generally. It's not a strict. It's the statement then. It's actually approximation. We say that those events when people in pizzeria die or give birth, they're very rare events, and we can neglect them in at first sight, and then we can sort of use that conservation law. But in principle, we cannot. So, and that's exactly the same story with everything else. If you have some chemical reaction and you're thinking about some molecules coming in, some molecules coming out, those are not necessarily the same molecules, right? If you write the mass current, then total mass is conserved, whether you have chemical reaction or not. But you can define your density, but not as mass density. I'll say oxygen density, right? Then oxygen comes in, but then it reacts right there, and something else coming out, and you don't count that. You only count the current of oxygen. Then it will not be conserved either, and the continuity equation will definitely not work, and you have to do something else with that, and so forth. So for majority of the properties which can flow, the continuity equation will not hold, or will not necessarily hold. It can be good approximation, it cannot be good approximation, but then you have to decide it for very specific problem. But there are special quantities which are conserved quantities when this continuity equation will always work, no matter what. It's charge, mass, energy, or whatnot. All those conserved quantities, momentum, angular momentum, and so forth. All right, so it's an exceptional property. That's what I'm trying to say. That's a very, very strong statement about the physical meaning of what is here, what is flowing. When we have continuity equation, what is flowing is conserved quantity. Okay, does that make sense?
Yes.
Yes.
All right. So let's then continue, and that's what we learned last lecture is what was called the Gauss theorem, right? And Gauss theorem tells you that for any vector field, it is any vector field. I use letter E for it, but I don't mean that it's electric field. I will mean it later on. That's why I use E. But for now, it's completely arbitrary electric field, completely arbitrary vector field. And for any volume omega, the flux through the boundary of that volume of that field, which is by definition is given by this expression. There's a definition of the flux. Must be equal to the volume integral of the divergence of that very field. Okay, so this is Gauss theorem. Now notice that it's very, very general. It tells you that for any smooth enough for any smooth enough electric field, for any smooth enough vector field, and for any piece of volume, that must be correct. And I hope that my example with that integral of the derivative actually helps you to understand that it's not really that complicated to imagine that it's so. But by itself, this is just a mathematical relation. It tells you that if you take any vector field and any omega, any volume omega, and you compute left-hand side, and then you take the same field and the same omega, and you compute the right-hand side, then what you will get, the number here will be equal to the number over here. Right? That's it. That's the only statement. It's a very powerful statement, but it has no physical content. It tells you nothing about this world. It tells you just about the different constructions, which you can do with some mathematical quantities. They actually, in fact, the same. They look differently, but they have always the same answer. Right? So it's a relationship between different mathematical constructions. The physical, there is no physical meaning here. There is no physics inside. Okay, because it's arbitrary electric field, vector field, arbitrary volume, and so forth, right? So don't confuse those things. It's the very power of this theorem is that it's very general and it doesn't have any physical content. So you can use it for any fields and whatever you can define. This just tells you that one mathematical construction equals another. So, but then that's called Gauss theorem. There is also Gauss law in electrostatics and electrodynamics also, and it tells you the following story: that if you have electric field now E is electric field, so it depends on coordinates, right? So we have some system of charges. As you know that all the charges produce electric field. So in any point of space, the total electric field is just vector sum of the electric field from all the charges. It can be a very complicated story, right? The charges can be very complicated in some complex arrangement itself. Moreover, what I want to do, I want to forget about that arrangement of the point like particles. I want to say that there is some density of charges in the space, right? So it means density of charges means that if I have some in some point R, right? So this is my origin, whatever it is, in some point R, I take some small, very small volume dV at this point R, right? Then the total charge inside that volume is that dV, the volume itself, times rho at the same point R. And so this is the total charge inside this volume. If I have that volume somewhere here, then this R is changing, the density is changing, so I need to take this volume multiplied by new number. So that's the total charge inside the volume dV. That's all. That's the charge density. All right. So now, I now have sort of two fields, right? I have that electric field, which is a vector field, and I have a field of density of charges. And it's sort of clear that they should be connected with each other, because it is charges, those charges, which produce that electric field. Okay, and so that's that connection between them is called Gauss law. Now, that Gauss law does have physical content because it deals with physical values. It's only correct for the electric field. And that Gauss law is the following: that if you have any volume omega, and you compute the flux of electric field through the boundary of that volume, it's exactly the same construction as this one. But this is for specifically for electric field. Right? Then the Gauss law states that physics of those charges and electric field are such that this flux always equal 1 over epsilon naught in the C unions multiplied by the total charge inside the same volume. Okay? So this is Gauss law. It has no relationship with Gauss theorem. The only thing is that we are dealing with the same construction. So Gauss theorem tells you that this equals to this, but here in the Gauss law we will only have this left-hand side. Right. So again, what is written here is if this is electric field, right? So we have completely arbitrary volume. It doesn't have to be sphere. It doesn't have to be anything. Well, it has to be smooth, but it can be completely regular. Whatever you can imagine doesn't really matter, right? So like something like that. So how we compute this? We split this surface, right? The boundary surface on small tiles. Each of those tiles will have its own vector ds, which is pointing outside, right? And perpendicular to the tile. In each of those tiles, at the same points of where the tiles are, we have electric field E, right? Then for each tile, we take the dot product of that vector E with vector ds, right? And then we sum them over all the tiles. That's what it tells us. That's what that construction is, right? So that's one. Now here, what is written here on the right hand side is that you take that volume omega now, not the boundary, but the volume itself. You split it on a little bit, very small pieces volume. You compute the charge inside that piece, right? It's rho times dV. Remember that's the charge inside that little volume dV. Here's little volume dV, and I computed the charge inside it, and then I summed that charge inside each volume and I summed over all those volumes. I compute the same thing for every volume, every small piece, right? And they sum them up. So what I will end up with is a total charge inside that volume omega. Right? Does that make sense?
Yes.
Yeah.
And the Gauss law states that the first construction will give you exactly the same number as the second. Now, this is a very, very physical statement. You see that those two things of completely different nature to begin with, right? This is electric field, and this is some density of charges. And what it tells you, that law, that the density of charges are connected with electric fields through this expression. So it tells you how electric charge produces electric field. Okay. So that's the Gauss. That's Gauss law, and that's exactly what allows us to compute actually electric fields for any system of charges. And so it also tells you, in some sense, remember that we actually can compute electric field by different way, right? We can take the system of charges, right, and split, but all of the charges, not just inside that volume, but all of the charges, right? Here, inside there, right? We have that raw. Okay, I didn't say that. The density of charge is not contained on inside that volume. It's everywhere. This volume has no relationship with anything else. That also volume omega is something which I just draw. I just imagine that there's just some surface here, right? For anything like that. So then we know how to compute electric field differently, right? We just say that if I have some density of charges here, then I take some small volume dV outside, and then I know the charge here, which is rho dV, right? And by Coulomb law, I know what kind of electric field this charge will make, for example, here, right? So I will know that little electric field which comes from that little charge, and then I just take those electric fields from all the points, and I sum them up. Right? So it means that I need to integrate. When I do that, I need to integrate over the whole space. Okay, and that will produce me electric field somewhere here. Over the whole space means that outside and inside also. Right. So everywhere I just take this integral and really compute this over all the space. That integral will not know anything about this volume whatsoever. It will not only know about this point. And that will be electric field, which is produced by everything, right? By all charges, which is inside and outside. The statement of the Gauss law then is very surprising. It actually tells you that if you now compute that electric field everywhere here, and that electric field again is produced by all the charges, not just the charges which are inside. But if I compute the flux through the boundary, it will still depend only on the charges inside that omega. And the flux will not know anything about the outside charges. Do you understand? Is it clear?
Yeah.
So this electric field, which is here, is a true electric field which you measure at this point. This electric field is a product of all charges, outside and inside. This electric field. It's a real electric field which you measure at this point. And yet, its flux depends only on the charges inside that volume. But only flux, not the electric field itself. If you know the flux, you cannot figure out what electric field is, right? Because that flux takes the electric field and then takes the dot product with ds, right? So you already lost some information. You already lost information about electric field which is perpendicular to the component of electric field which is perpendicular to ds, to ds at each point. And then what you do, you actually summing it over all surface. So you don't know the value of the electric field. You only know the sum of its components around the whole surface. So it's impossible from this law, generally speaking, to take electric field to figure out what electric field is. Okay. So in this sense, that's why it's called sometimes global version of the Gauss law, which is very difficult to use because at the end of the day, we usually what we want is if we have some distribution of charges, we know some distribution of charges, we want to know what electric field it produces in each point. Right? But what it tells you is that not electric field, but some flux of something, right? It's not very useful in this regard. But nevertheless, it's a very strict statement. I will show later on how to use it to compute electric fields. But now, I want to say that there are 3 examples which I know of, which tell me, which actually gives for which that's enough to compute electric field itself, that law. But there is only 3 examples of those things, and and this is possible because those examples have very high symmetry. So the first example is of course a sphere. Let's imagine a sphere which has a charge q, and I want to compute what is the electric field distance r from the center of the sphere. Right? This charge q it's uniformly distributed around the sphere, and you can and the sphere is not hollow. It's a total thing. And then now, if I want to use Coulomb's law, what I need to do, I need to split that sphere in little pieces. Right? Then I have uniform distribution of charges, so that my rho does not depend on the position. It's just a number. So then, on each of those, so that volume has vector little r. Let's call that vector. Let's call it capital R, right? And then what I need to do, I need to say that electric field which is produced by this piece of volume is rho dV times that k, right, divided by the square of that distance. Right? The square of this distance is r minus little r, and I need to take square of it. Right? And that electric field will have some direction like this. Well, it's along this line, sorry. Like this. Okay? So I need to then to take the components, different components of that electric field, and it can be done by doing it this way. So it's r minus little r here. Yes, sir. So it's actually three different quantities here. If I write on the components, right? And then after that, I need to sum them up over the whole sphere. All right. That makes sense? So I can do that from Coulomb's law. Because remember, the Coulomb's law tells you only about the electric field through from a point-like charge. So I have to use only point-like charges. And this little volume here is almost point-like charge. So then I need to take this integral. That's not a simple story. It's possible to do this integral. It's possible to take it by hand, but it's not a simple exercise. So, but you see that the story here is though that this is a very symmetric distribution of charges. So what it means symmetric is that if I now take the distribution of charges, right, and I compute the electric field here, and I rotate this distribution of charges around any axis, nothing will change. The distribution of charges does not change under that rotation, right? Right?
Yes.
Yes.
It's just a sphere, right? You look at sphere from any side, it's the same thing. So and if my distribution of charges is uniform inside the sphere, that when I rotate it, nothing, the distribution of charges does not change. If the distribution of charges doesn't change, it means that electric field will not change. Right? Because electric field depends only on the distribution of charges. Well, first of all, it means that electric field must be along the radius. Right? Because if it has some angle like this, if I now rotate my distribution of charges around this axis, then this electric field will rotate. But it must not, because it must stay the same under this rotation. The only way to do that is to say that electric field must be along the radius. Okay? Does that make sense?
Yeah.
Now, it also must depend only on this distance. Right? It cannot depend on any angles here. Simply because if I, for the same consideration, now if I have electric field in this point, now if I rotate everything around that z-axis, right, then this point will come over here. And it must have the same electric field. So the electric field, that electric field which is produced, must have the following form: some function of the radius itself multiplied by the radius, vector of radius, right? So this is a vector, something like that. This is the only way to keep the symmetry. Okay? And now I can actually use this theorem. If it is so, then let me choose. You see, remember that this omega, that volume, is any volume I want. All right. So if I choose that now this surface, this sphere of radius r, capital R, as my surface in this integral, then let me compute the left-hand side and right-hand side. So the left-hand side, then I have electric field. I have small ds here, right? So this is ds. The vector of ds is exactly along the radius, right? Because the little piece of sphere is always perpendicular to the sphere, to the radius. Now my electric field is also exactly perpendicular to the ds. Perpendicular to this electric field is along the radius, so the vector of ds and vector of electric field have the same direction. Right? So instead of that dot product, I can write just E, the magnitude of E times the magnitude of ds. There is no angle between them, so cosine of 0 equals 1. And now I need to sum this up over all this surface. Right? But electric field, the magnitude of electric field will be the same everywhere. So I can pull it out of this integral and write it like this. Right? But then what I see here is just the total area of my surface. The total area is, of course, so I have E, and the total area of the surface is 4 pi r squared. So this is the left-hand side of this this equation. Now the right-hand side, I need to compute the right-hand side now. And the Gauss law states that they must be the same. But the right-hand side is just the total charge. But the total charge here is Q. So what I have is here is Q divided by epsilon naught. Okay. And so what I have here is that in this particular case, for this problem, E equals the magnitude of E equals Q divided by 4 pi epsilon naught 1 over r squared. 1 over r squared. Or if I want to now to write it as a vector, then I need to multiply it by vector r, because it's along the vector r, and then I need to put here r cubed. So the magnitude doesn't change. Okay? That makes sense?
Yes.
So this is something which you know, but what I want to emphasize here is that the high symmetry. This is a symmetry, very high symmetry of the charge distribution, which allowed us to compute this integral and express electric field from the integral itself, which is normally not the case. You cannot do that. All right. So it's in a sense like you can think about it as taking the integral is like taking an average, so it's like you cannot figure out what is your own grade if you only know the average grade of your class, right? It tells you nothing about your own grade. The same thing here. If you know only the integral, it tells you nothing about the electric field in any particular point. Okay, that makes sense?
Yeah.
All right. The next example, which you also know, is the plane, the charge plane, and it's infinite plane, and it has a charge density sigma. Charge density sigma means that if it's a surface density, right? It means that if I take any area here, ds, right? Then the charge inside this little area is ds times sigma. Right? And that sigma is uniform, so it's the same everywhere. It doesn't depend on where exactly on the plane I am. And then you ask what is the electric field from this infinite plane. And again, we can use the Gauss law in that integral form to compute it. But again, only because there is a very, very high symmetry. And that very high symmetry tells you that if you take that infinite plane and you rotate it around this axis, any axis, right, the distribution of charge does not change, right?
Right.
Yes.
So it means that the electric field must be either this direction or this direction, perpendicular to the surface, to the plane itself, right? Because that's the only way when it doesn't change. Now, if you take infinite plane and you shift it around, right? So you shift it parallel to itself. It's infinite, right? So it means that there is no difference between before shift and after shift. And so what it means is that electric field should be the same everywhere, right? Now you can also think about it that if I now measure the electric field at this point, right? Then from this point, I see some distribution of charges. Let's imagine that I'm sitting in that point, just a little bit above that plane. And I look around and I see some distribution of charges, right? And that distribution of charges produces electric field at this point. Now imagine that I went up a little bit, okay? Maybe not a little bit, but 1 meter up. And I'm still looking at the same distribution of charges. And what I see is exactly the same distribution of charges as before. Because the plane is infinite. If it had finite size, then when I move up, I see it sort of shrink, right? The plane. That makes sense? But when the plane is infinite, I don't see any difference between the distribution of charges before I moved up and after. So it means that the electric field must not depend on what is the height of that point with respect to the plane. It should be just a uniform field. Right? So those are symmetries of the problem. And those symmetries now allows us to use that theorem. So to use that theorem, we need to choose some surface, right? Some volume. And then you need to be clever and see that that volume should probably have the same symmetries as the rest of the problem. So let me choose some can kind of volume, right? So it's a can which goes through that surface. So it's a cylinder like this, right? Which penetrates through the surface. Is it clear?
Yes.
You can think about like a Coca-Cola beer can, which penetrates like through a piece of paper, whatever. So now let's say that the length of this is some, I don't know, h. It will not play any role, and the area of that cylinder, this area is S. Right. Then we need to compute the left-hand side of that Gauss law, and the left-hand side tells us that we need to have electric field, which is this direction, and S, which is now also the same direction, right? So we have S times E, right? This is the flux through this part of the cylinder. Now, from the sides of that cylinder, there is no flux because the electric field here is going up or down, but the vector of S, the vector of area, is perpendicular to is horizontal, right? So it's perpendicular, so the dot product is 0. And now there is one more thing is the bottom part of it. It also has area S. The area is also going outside, so the vector of area is down. the vector of electric field is also down, right? So the flux through this part is just the same thing. Okay? So this is the total flux of electric field through the surface. And that total flux of electric field through the surface must be equal to 1 over epsilon naught, and then we need to compute the total charge inside this volume. And the total charge inside this volume is the charge on this little circle which we punched out, and its charge is sigma. The charge density is surface charge density times S, the area inside here, right? That makes sense?
Yeah.
So what we see here is that S cancels out, as it should, right? Because it's arbitrary surface which we draw, and electric field should not depend on the arbitrary surface. And what we have now is that electric field equals sigma divided by 2S. Okay?
Wouldn't that be sigma divided by 2 epsilon naught?
Say it again?
Wouldn't that be sigma divided by 2 times epsilon naught, not S?
Oh, thank you very much. I try to talk faster and I make mistakes. Yes, of course, epsilon naught. I'm sorry, S cancels out. I just said it. Yeah. Thank you. All right, that makes sense?
Yes.
Yes.
Now it should. Before it didn't, actually. All right. So it's now you can compute electric field if you know the distribution of charge, the charge density, but only if the charge density is uniform and the plane is infinite. Otherwise, it will be. You can think of it as some sort of approximation, and then you need to look whether this approximation works or not, and so forth. Now, there's a third example is when you have a charged wire, straight wire, infinite. All right, and there is some charge, and this charge density rho, and now it's linear charge density. What it means is that if I have a little piece here with length dx, then the charge inside that little piece is dx times rho, right? And that rho is the same everywhere on the wire. And then I want to compute what is the electric field here is. And then what I have is electric. So again, if there is electric field here, it can depend only on this distance, right? Because it cannot depend where it is, right? Because I can shift always that wire, and it's infinite. So the density of charges does not change up under the shift. So the electric field can depend only on that distance r, and it also must be perpendicular to that r, right? Because I can always flip that wire around, and distribution of charges does not change. And it also cannot depend on the angle around the wire, because I can rotate the wire around its own axis and nothing is changes. And so the electric field then is along. It depends only on r. It's along that radius, along straight out away from the wire. So in this point, it will be pointing towards you, and this point it will be pointing towards there, and so forth. So again, I need to choose a surface which has the same symmetry, and this surface is a cylinder. This is my surface, the cylinder of radius r, capital R. Now, the electric field everywhere, again, is perpendicular to the surface. And it means that the dot product is, of course, is again trivial. It's just magnitude of E times the surface. Electric field has the same magnitude everywhere. So again, when I compute the flux, I can pull it out of the integral, right? And all of that only because of the symmetry. And then my flux is electric field times the area of the cylinder. So if this length of the cylinder is capital L, then the area is 2 pi r times L. So this is my flux. and that must be equal to the total charge inside the cylinder. And so it's 1 over epsilon naught, and the total charge inside is just L times rho. Right? And so that's my equation. Again, L again cancelled out, as it must. And what I have here is that electric field will be equal to 1 over 2 pi epsilon naught, and then I have rho divided by r. Right? This is the magnitude of electric field, and the direction is always straight away from the wire. Right, so this is the only 3 problems which I actually know of, which can be solved by using that global version of the Gauss theorem, and that's because all that you can only use it if you have the global version through integrals. Only if you have some symmetry which enforces some other constraints of electric field. Like electric field cannot depend on the angle and so forth. Those constraints are enforced by symmetries. If it's not there, if there is no such constraint, that's it. There is no luck. You cannot do that. You cannot use that formula to that law to actually figure out those electric fields, right? But it's nevertheless it should be possible to solve for electric field if you know the total distribution of charges, and it is. There is another formulation of that law, right? So what we have so far is the formulation which is global formulation, which states the following: that the total charge over some closed surface equals 1 over epsilon equals the total charge inside the volume which enclosed by the surface. Right? So that's our Gauss law. But now what I want to do, I want to use that Gauss theorem. I know that whenever I calculate this, I will always get the same answer as this one. So I want to use the Gauss theorem over here and rewrite it as the integral over total volume as a divergence of electric field dV. Right? So this is a Gauss theorem here. It states that for arbitrary vector field, arbitrary omega, I will always have this construction. But now what I have is that this one must be equal to this one. Right? So what I have now is the integral, and now let me move them on the same side. And what I have is divergence of electric field minus rho divided by epsilon naught integrated over dV. Right? And this integral must be taken over omega, and it must be equal to 0. Right? So I just take this equation, this equals to this one, and move them on the same side. Does that make sense? Now notice I could do that because it's integrals over the same volume, right? So then I can move the sign of the integral up. But now I remember that it must be correct for any volume whatsoever. If it is correct for any volume whatsoever, it means that it must be that what's inside here must be equal to 0. Right? So it gives me the local formulation of the Gauss law, which is divergence of electric field at any point must be equal to rho divided by epsilon naught at the same point. Right? So what it means is that if I have some point of space and some electric field, and if I compute the divergence of electric field at this point, just what is written here, right? Just what we did in homework, right? So this is my point. This electric field. I compute divergence of electric field exactly at this point. The divergence of electric field exactly at this point must be equal to the density of charges in this point again, divided by epsilon. Okay. So the divergence of electric field at any point depends only on the electric charge density at the very same point. So that's why it's sort of it's local formulation of the same law. Those two laws are exactly the same. But this is a global formulation that talks about integral. This is local formulation. Everything happens exactly in one point. Okay? Does it make sense?
Yeah.
Yes.
All right. So, and now that's the third homework problem. Now, it can be kind of surprising because electric field here at this point. Now, remember that I said electric field at this point. I didn't say that it's electric field due to the very same charge. Not at all. It's electric field which you measure at this point. The electric field at this point is produced by all other charges. Right? And that electric field, the total electric field, the divergence of the total electric field will be equal to this one. To the charge only in this point. Does that make sense?
Yes.
And the reason for that is exactly your homework problem number 3. Because all of other charges, I can consider them the point-like charges, but the divergence of electric field from a point-like charge equals 0. So if I have some point of space where I do not have any charge whatsoever, so let's say that rho at this point, at this particular point, rho equals 0, then according to this, the divergence of the electric field must be 0 here. Right? But it also, but we already know that because all that electric field, which is electric field itself is not 0 here. Electric field is something. It is produced by all other charges. But electric field produced by all other charges has divergence equals to 0. And that's exactly what was the third problem in homework about. Right? Does that make sense?
Yes.
All right. So it can be, but you can also do it the other way and say that, well, if I have now point-like charge here, Q, right, it produces electric field everywhere, and there is no more charges, right? Then what that law tells me is that if I measure electric field at any point, there is no charge in this point, right? The charge is only here. So the electric field which is produced by this charge must be such that the divergence of electric field everywhere equals 0. Okay? But the flux of electric field, if I now compute, if I now take any surface like this, the flux of electric field must not be 0 because of the global version. The flux through any surface which contains this charge inside must be equal to the charge to the Q divided by epsilon naught. Okay, so the divergence of electric field is 0, but the flux through any surface is not 0. And you can actually, and it looks like it contradicts this way, right? The divergence everywhere is 0, so that we have, it looks like this integral must be 0. But if that integral must be 0, then the flux must be 0. So it looks like it contradicts the Gauss theorem. Right? Do you understand?
Yes.
Right? So if I say that divergence everywhere is 0, then how come this integral is not 0? What it means is that it's only possible if there is a singularity inside. So that electric field somewhere must be not smooth function anymore. And that's exactly correct for Coulomb's law, because exactly at the point of z charge, right? The Coulomb's law, electric field diverges. There is no you cannot write a divergence of electric field. You cannot take those derivatives exactly at this point. This is why exactly at this point, this theorem is actually you don't know what this integral is, because there is no such object as the divergence of electric field. And now if you take the electric field due to Coulomb interaction, you can actually, due to Coulomb law, you first of all, we know already from the homework problem that this is satisfied for the Coulomb law, right? Divergence everywhere equals 0. But we also can directly compute what is the flux of electric field through any sphere of radius r, right? Electric field there is equal to kq divided by r squared, right? And it's perpendicular to the along the radius. So all I need to do is to compute this flux. All I need to do is to multiply this electric field by the total area, which is 4 pi r squared. And what I see here from 4 pi r squared. And what I see here is that r squared cancels out, and I have a constant, some non-zero flux, right? So the Coulomb electric field actually does satisfy this equation everywhere, but there is a special point where you cannot compute that what is divergence of electric field is, and but you can use the global version of the theorem, and it actually then you see that it is satisfied. And this is the only reason for that is that I said that this point is the charge is a point like, right? And that's what gives me in mathematics always gives a problem when something is point like, and then you can have singularities there. If I say that the charge is some little sphere, then I actually can use directly this equation and compute electric field everywhere without any problems. Okay, does that make sense?
Yeah.
So this is Gauss theorem, Gauss law for electric charges. But instead, in addition to electric fields, there's also magnetic fields, right? And this law actually tells you that electric charges are the sources of electric field, right? So it's what it tells you that divergence equals to the charge. So you place the charge inside, and it produces a divergence of electric field. So the charges, the electric charges, is the sources of electric field. But with magnetic field, there is no magnetic charges, right? There is no, in our universe, is magnetic charge. It's a huge mystery why it is not. No one knows. There is no answer for that. We're still working on it. And but we know from experimental situation is such that we never see them. Those magnetic charges, right? So we can assume that we don't have them. And if you don't have magnetic charges, but we can then if we try to write the same law for the magnetic field, what we will have then is that for any omega d omega b dot ds, where now this is magnetic field, right, must be equal to the total magnetic charge somewhere. But magnetic charge are zero, magnetic charges are zero, so it must be equal to zero. And that's exactly the Gauss law for the magnetic field. And by exactly the same procedure as before, just using Gauss theorem on this integral, you can write that the local form of that Gauss law, that magnetic divergence of magnetic field always equals to zero. Because just so notice that it's exactly the same law here, with additional statements that there is no magnetic charges. Okay, does that make sense?
Yes.
So again, let me reiterate it a little bit and just say that this is Gauss theorem. It works for everywhere, for any smooth vector field. This is Gauss law, which tells you how electric field is connected with the distribution of charges, right? But in this form, that law is very geometrical, but it's difficult to use. And by using Gauss theorem, we actually can rewrite that law in terms of the local properties. And this is now a differential equation for electric field. And the differential equation must be supplied with some boundary conditions, and then we can solve it. And for any rho, for any distribution of charges, we then be able to find what electric field is. Right? And here we have a magnetic field, and the same story for the magnetic field, but the only difference is that there is no magnetic charges, so the right-hand side of those equations always equal to zero. Okay, so those are two laws for electric and magnetic fields. Those are not enough. We'll consider the two more of them, Faraday's and Ampere's law, next lecture. And well, that's it for today. Any questions? Any questions?
Wait, can you hear me? So the gradient of E is.
I cannot really hear you. There is a lot of noise. Hello?
The gradient of E is only non-zero because there's a charge source.
It's divergence, not the gradient, right? Gradient cannot work on vectors. For vectors, this is a dot product here, right? So yes, the divergence of electric field is zero everywhere if there is no charges, and if you have a point like charge somewhere, then the divergence there will not be zero. And if you have some distribution of charges, right, then the divergence of the electric field will be equal to the density of charges at the very same point. So that's exactly the story, that electric charges are the sources of electric field. Divergence of vector field means that it's sort of going like this from a point. Right? And what it tells you is that there's any charge which sort of produce electric field which will go outside. So it really means that electric charges are the sources of electric field.
Okay, thank you.
Any more questions? All right, then that's it. And thanks for coming. And see you on Monday.
Thank you. See you on Monday.
Thank you.
Thank you. Thank you.